Okay, now we're looking at chapter 10 in your workbook. It's page 113. You can either print out the pages or just write in a notebook. I would encourage you, make sure you're checking out the textbook. Do that required reading first. Probability can be a bit tricky. So it starts on page 335 in your book. We're just going to do the first couple of sections. So section 1 is talking about just the basics. A specified event is the chance or likelihood that the event will occur. Experimental is a repeatable process, the experiment, and that's when we actually collect data. And you'll have several trials, and the more trials you have, the closer and closer you'll get to the theoretical that we'll look at as well. So theoretical is we're talking about the possibilities of something occurring and over the total number of possible outcomes. So it's pretty much the same idea. You're just taking the number for the event over the total, but it's how we set up the sample space might be just a little bit different. So some basic concepts here. The result of an experiment is called an outcome. So that's a big vocab word there. Event, sometimes we just use capital E, like flipping a coin and getting a head, like head, that would be the event. If we flipped it 3 times, we would say the event is getting a certain number of heads out of that, when we would choose that. Like I got exactly 2 heads, or at least 2. So we use a lot of language like that. Simple event is we just have one outcome. A sample space is a set of all possible simple events when you put them together. Okay, so now we're on page 113 still of your workbook. If you printed out the workbook ahead of time and not the pages that I scanned in with the lesson assignment that you're taking notes from, this is just from the teacher textbook, so it's lined up just a little bit differently, but it has a larger font, so that's why I'm using this. So I've marked the pages just in case. So we have, suppose we roll a fair 6-sided die, one at a time. What is the sample space for rolling a die? So if it's just one and we're not having pairs or threes, then it's pretty simple and straightforward. But how we would write that, we could write a capital S for our sample space, and then we're going to use our set notation with the braces, and it would be the set of 1, 2, 3, 4, 5, and 6. So that's how we would list it out as a set. So sometimes words or descriptors as well. But if we want to see each individual item, we would write it that way. We also, like in the set chapter, we talked about cardinality. So a lot of times in probability, we just want to see how many numbers, how many items or elements. So in this case, we have 6. For our number in the set. Then here is a little formula for you. Basic probability. Given that all outcomes are equally likely, we can compute the probability of an event E by the given formula. So equally likely just means that it's balanced. There's not a weighted die or something on it that's making it turn that to that side more than another. So if I had an extra 6 in there, for instance, on the somehow, in place of a different number on one of the die, like it was a trick one or a fake one for cheating, that would affect it, and it wouldn't be equally likely. So we do need to often preface that, but that's all that means, that it's fair. So we have our probability is the number of ways event E can occur. So we can write that, abbreviate that as number of E, and then over the total outcomes, which we could do the number of the total sample space like that. So what is the probability of rolling a 3? Well, we have probability of a 3. That's how we can write that with the P. And our event is the 3. So that occurs one time in the set that we were just talking about out of 6 total possible other outcomes that could happen. So we always want to reduce. This one's already reduced, but we could convert to a decimal if we want. A lot of times we leave it as a fraction depending on the problem though. So it would be 0.166666, so on forever. So we're just going to round to 3 places. So we're using our approximation symbol, and either of these answers is fine. About rounding, you want to round to 3 significant figures. That just means, I could post something about that, but basically if you have a really tiny number and you had like 0.000000123, you would want to put all of that, because you can't just put round 3 places, you would have 0.000. So you have to go far enough out for comparison purposes and to see what it's doing. I am going to let you do these right here, B and C, as classwork. So pause the video and just do those right now, and then check your answer right away, whether you're doing it in a notebook or right on the workbook. Please make sure you mark everything clearly, and also do make sure all your pages submit. A few people I've noticed only one page is showing, so do make sure and double check that. Okay, so here's the answers for probability of rolling a number larger than 4. We would just have 5 and 6, not including 4. This is how we could write this. We would have 2 over 6 and then reduce, and we can round off to 3 places here, 3 significant digits. One thing we can also do if you wanted to is to just convert it to a percentage by moving 2 places right. Usually we go to the nearest 10th or 100%, so we can just carry that a little further. This one here, number of evens, 2, 4, and 6 are even numbers on the face of a die. So probability of evens, 3 out of 6, reduce, and then you could just say about 50%, or exactly 50% on this one. Okay, in probability, we use a lot of cards and things like that to calculate probabilities and to figure out what our likelihood is of, when we're gambling and things like that. There is a chart in your textbook, so just make a note of that if you haven't played cards lately. See page 338 in the textbook. Just write text, and there's a chart there of all the cards laid out. So there are 52 cards in a standard deck. Bucky has a deck of cards. He wants his friend Satchel to draw a card. After Satchel draws a card, he puts it back in the deck. What is the probability of Satchel drawing an ace from a deck of 52 cards? What does it say about probability of drawing one type of card? So we would have probability of an ace. And if we hadn't just been using the formula, you should write it out. But for this one, we know it's just there's 4 aces, number of the event, over total possible cards in a deck. And then we're going to reduce that to 1/13, or we could round. A lot of times with probability too, we also drop this front 0 there. And that would be about 7.69% if we wanted to write it as a percentage. What does this say about the probability of drawing one type of card? So if we were talking about the types being a number or an ace, it's not really very clear, but I think this would apply to all of them because there's 4 of each number or ace or face. But if we were talking about suits, that's a little bit different, and you'll have some problems pertaining to that, or colors as well. So this one here, example 10.4, a survey was taken of drivers admitting to running a red light in the last year. The number of yes responses was 500. So we have 500 yeses. The number of no is 213. Find the probability that if a person is chosen at random, he or she has run a red light in the last year. So we would need to find our total first. We're not given the total of people asked, but we can figure it out. You did some things like this back in the beginning unit. So we would have our event is the yes responses, people that admitted. So probability we could say of yes is 500 out of 713. That's up quite a bit. This is reduced. You could use your fraction key to prove it out, but you can just use a decimal. We really don't want to round within a problem. Like if we had more steps to do, we would leave it as a fraction, or if we calculated it out as the decimal, we would leave the decimal in our calculator before we do the next task. And we could write this as a percent, 70.1%. That's quite a bit. If we wanted to go 2 places, we might say 3. So this is some data that we're given so we can make predictions from it, and when we do statistics, that'll be helpful for that. Some things to note here, probability rules, that we would never, in a possible event, we wouldn't have any probability of that happening. That would be 0. If it's always going to happen, 100% of the time would be 1. Probability of any event must be between 0 and 1. So that's an always thing. So if you end up getting a negative answer for some reason, if you had to crunch some numbers and use algebra and you end up with a negative, then that is not going to work. Also, all your probabilities for separate events within the same thing that's happening, though, the simple events, when we put them together and have compound events, the probability should always add up to 1. So if I were to take, like with the card problem, if I had all the different cards and I had added up, okay, probability for the aces, probability for the kings, and so on and so forth down the line, I should get 100% if I were to add all those probabilities together. Same thing here, probability of a yes, its counterpart, probability of a no, that should add up to 100. So we can use that idea of how things add up to 1, and that's called the complement, which we'll look at next.